Hey, linear algebra students, welcome back. This is the last week of classes. Today is Tuesday's lecture, so if you're keeping track of schedule, what we have is lecture new material today, new material on Thursday. We're going to review on Friday, and then, so that would be Friday let me look at my calendar, Friday the 5th, and then our exam is 1 week from that, which will be Friday the 12th of June is when our final is. And during finals week, I will hold office hours. I guess let's just do the usual thing. So I'll do it Tuesday and Thursday. So that would be what, 1 to 2:30. So during finals week, office hours will be exactly the same as usual. Tuesday, Thursday, 1 to 2:30. Okay. All right. So let's see. We started talking about inner products in the last lecture, and so we want to continue with that discussion. And we're going to start with a famous theorem, and it's called the Cauchy-Schwarz, and I gotta remember how to spell this, S-C-H-W-A-R-Z inequality. All right, so the Cauchy-Schwarz inequality, if, it goes like this, so if V is an inner product space, then the absolute value of the inner product between any two vectors u and v is less than or equal to the norm of u times the norm of v. Right? So this inequality right here, it's known as the Cauchy-Schwarz inequality. Remember, an inner product can be positive or negative, so we need to take the absolute value on the right-hand side. Sorry, on the left-hand side. Now, as a consequence, so here's the statement of the theorem, but a consequence if we unravel this this statement here, getting rid of the absolute values, what we have is negative norm of u times norm of v is less than or equal to the inner product of u with v, which is less than or equal to the length, or the norm of u times the norm of v. Now, assuming that u and v are both non-zero, I can divide, so let's say when u not equal to 0 and v not equal to 0, both here are the 0 vectors. So when we're not thinking of the 0 vectors, then what we have is, so we get, let me put it up here. So what I'm going to do is I'm going to divide all sides of this by length of u times length of v, and what we get is minus 1 less than or equal to inner product of u with v divided by norm of u times norm of v less than or equal to 1. So what we have is that this fraction right here, as long as it makes sense to divide by these numbers here, right, as long as they're both non-zero, right, this fraction right here is between plus and minus 1. If you want, there's the proof. The proof of this inequality, this theorem is in the book, so you can check it out. It's really just a computational thing. The consequences are easy, but what this tells us now, right? We have this fraction lies between plus and minus 1. This is going to allow us, and I hinted at this last time, this allows us to define the notion of angle between two vectors in a general inner product space. So we can say thus, for every, let's say u and v in V, there exists a unique, well, I can't say unique unless, well, let's see, I don't want to word this. Yeah, forget the uniqueness part. There exists a number theta between 0 and 2 pi such that cosine of theta is equal to inner product of u with v divided by norm of u times norm of v. I guess I do have to say here every u and v that are non-zero, right? So what's the point here? We know that cosine lives between plus and minus 1. And so that means that every time we have a u and a v, we can compute this number right there, and there will be some theta between 0 and 2 pi. So the cosine of theta is equal to that. And so this gives us a notion of angle. That number theta right there is the angle between the two vectors. So theta is the angle between u and v. So this generalizes the idea of angle that we have when we're working with the Euclidean inner product, the dot product in Rn. So for example, let's find the angle between the polynomials equal to 1 plus x, and q of x is going to be x plus x squared in P2. Here, I want to use the standard inner product. Right, we actually know that there's lots and lots of inner products. There's various weighted inner products or sample inner products on the space of polynomials. But I want to compute the angle in the case that we're dealing with a standard inner product. So what do? I say, all right, what we have is cosine of theta is going to equal the inner product of p of x with q of x divided by length of p of x, or norm of p of x, and norm of q of x. Right? So I need to compute the quantity on the right-hand side and then figure out what theta is going to be. So let's see, I'm going to continue the equals over here. Okay, so the inner product of p with q is going to be, well, it's going to be 1 times 0 plus 1 times 1, so it's just going to be 1. The length of p is root 2. The length of q is also root 2. And so what we get is 1/2. Right? So we have cosine of theta equal to 1/2. That tells us that theta is pi over 3. So there is the angle between the polynomials p of x and q of x. It's strange to picture what that means. I mean, what is the angle between a couple of polynomials? Well, this is a way to actually get at the idea of angle between vectors when they don't look like arrows that we're used to seeing in Rn. So another definition then, and this should remind you, I mean, when you're working with vectors and working with a dot product in R2 and R3 in Math 143, the next thing that happens is you define this idea of orthogonal. And so vectors u and v in some inner product space, I'll just say in capital V, are orthogonal if their inner product is equal to 0, right? You learned this definition of orthogonal back in Math 143, and it corresponded to having the dot product equal to 0. So now we're generalizing the idea of orthogonal, right? You want to think of it as that the vectors meet in a right angle, right? And it will happen when we get an inner product of 0. So for example, with respect to the standard inner product on M sub 2, 3, the matrices A equals 1, 0, 2, and second row negative 2, 1, 3, negative 2, 1, 3, and B equal to 0, 2, 3, 1, negative 1, negative 1, 1, negative 1, negative 1. So these two, these are orthogonal. I think I actually already computed their inner product, but let's just do it real quick to remind you. All right, so how do we verify this? The inner product of A with B is the trace of A transpose times B. Right? So when we multiply this, so if I compute A transpose times B, that's going to be A transpose, so 1, 0, 2, negative 2, 1, 3, 0, 2, 3, 1, minus 1, minus 1. All right, so when we do the matrix multiplication here, let's see what we get. I'm going to get a 1. I'm going to get a 2 plus 2, so that's 4. I'm going to get a 3 plus 2, so that's a 5. Then I'm going to get a 1 minus 1 and minus 1. Then I'm going to get a 2 and a 4 minus 3 is 1, and then a 6. Six minus 3 is 3, so hopefully I did something wrong here. Let me back up. Oh, right. Sorry, that very first entry right there, that should have been a negative 2. Sorry about that. Okay, so here is A transpose B. It's this matrix right here. And then to compute the trace, what do? You add the entries on the diagonal. And so that is equal to 0. When you get an inner product equal to 0, you say that the corresponding vectors are orthogonal. So, although it's very strange to picture, what this is telling us is that these two matrices right here in M23 meet at a right angle. A couple more examples. We did this well, let me think, didn't we? Oh, no, we don't. Never mind. So another example, cosine of x and sine of x, and sine of x are orthogonal in C 0 to pi. Remember, that's the space of all continuous functions from 0 to 2 pi. And how do you verify that? Well, remember, the inner product of cosine x with sine x is the integral from 0 to 2 pi. So remember, you integrate over the interval, right, and you multiply the two functions. So this would be cosine x times sine x dx. You integrate this by substitution. So if you let u equal sine x, you get du equals cosine x dx. And so this becomes integral from 0 to 0 of u du, which is, of course, 0. Right, so that tells us that these two functions, cosine and sine, are orthogonal within the space of all functions, continuous functions, from 0 to 2 pi. One more example, and this is just to remind you that orthogonality, in fact, angle in general, depends completely on the inner product that you're using. Right, so let's just look at an easy example here. In R2, let's take u equal to 1, 1, and V equal to 1 minus 1. Now, let's talk about a couple of different inner products on R2. The first one, the standard inner product, the Euclidean inner product. So with respect to the Euclidean, which is just to say the dot product, so with respect to the Euclidean inner product, U and V are orthogonal, but with respect to the inner product, so if we do the inner product that's weighted, and let's do 2 U1 V1 plus 3 U2 V2, we have, for this particular choice of U and V, let's see what we'd have. We'd have 2 times 1 plus 3 times negative 1, which is not equal to 0, so they are not orthogonal with respect to this inner product right here. Right? So orthogonality and angles in general are completely dependent on which inner product you're working with. You notice I'm holding my shoulder. Something's wrong. I don't think it's rotator, but it's been getting worse and worse, so I'm glad that the quarter's almost over so I can go get this taken care of. Anyways, it really hurts to write, so if I get slow or moan or groan, just bear with me. So let's let W be a subspace of some inner product space V. So I want to highlight the fact that this is an inner product space. The orthogonal complement of W is, and remember we saw this a little while ago when we were working with the dot product. Now we can define orthogonal complement in general. So the orthogonal complement of W is the space W perp consisting of all vectors in V such that all vectors, sorry, I need to fix that. All vectors, let's say little w in, no, let's say all vectors v, little v in capital V, such that V is orthogonal to all vectors in capital W. So W perp is the set of all vectors that are orthogonal to everybody in W. I can write this using set notation. Right, W perp equals the set of all V such that V inner product with W equals 0 for all W in W. Right, so the way you want to picture this, right, so inside V, so V consists of all this stuff. If we take some subspace W, right, then W perp, I mean, this is as good as I can do. This is sort of the schematic here of what W perp looks like. It's the set of all vectors that are orthogonal to everybody in W. And we can check this. I'm going to write this down as a theorem, and maybe we'll prove one of these. Well, theorem. If W is a subspace of the inner product space capital V, then 3 parts to this. So first, W perp is a subspace of V. So the orthogonal complement of a subspace is a subspace itself. The second part is that if we look at the intersection of W and W perp, the only vector that they have in common is the 0 vector. And let's see, the last piece, the orthogonal complement of the orthogonal complement is equal to W. So W perp is equal to W as long, this is true, as long as V is finite dimensional. So if dimension of V is finite. I don't actually think we need to, I'm not going to bother with proving this. These are good exercises for you. In fact, maybe I'll assign these. I haven't written down your homework yet. Maybe I'll assign some of these as homework problems. But for part A, you can see we did this already. We proved this for the dot product, and so the proof is almost exactly the same. Now, so let's do a little bit of, let's do some examples here. So let's say in R4, let's let W equal the span of the following set. So this is going to be 1, 0, 1, 0, and 2, 1, 0, 0. Now, we know that W perp is a subspace of V. What I'd like to do is find a basis for W perp. So let's find a basis for W perp. Now, the way I want to go about this is I want to say, all right, if you are a vector in W perp, oh, and sorry, I've got to say using dot product or using Euclidean. So Euclidean inner product. Right? This answer would be different if we use some weighted inner product. Right? So problems like this are definitely dependent on the inner product that you're working with. Okay. So what we want to do. So let's say we have X, Y, Z, W. So if this is in W perp, then what do we know? That means that this vector, here's a general vector, has to be orthogonal to everybody in W. In particular, we know that this vector would have to be orthogonal to both of these vectors right here. So then we would know that X, Y, Z, W dot 1, 0, 1, 0, which by the way is what, X plus Z, that has to equal 0, and X, y, z, w dot, the other one, 2, 1, 0, 0, 2, 1, 0, 0, which equals 2x plus y, that has to equal 0 also. Okay. So what this does then is it gives us a homogeneous system. So this is a homogeneous system, and I'm going to write down the augmented matrix here. So that will look like 1, 0, 1, 0, 0, and 2, 1, 0, 0, 0. All right, so there's the whole, and what we're looking for then, W perp consists of all such vectors, which means that W perp is the null space of that matrix right there. Okay, so now what I'm going to do, let me get this in reduced row echelon form, and it goes like this: 1, 0, 1, 0, 0, and 0, 1, negative 2, 0, 0. All right, so if you go through the steps, here's the reduced row echelon form, and now we can write down a basis for the null space, and the basis for the null space corresponds exactly to the basis for W perp that we're looking for. So we got two free variables here, x3 equals s, x4 equals t, and then x1 equals negative s, and x2 equals 2s. So a general vector is going to look like, oh, you know what? This is really x, y, z, w, huh? Sorry, let me just, to be correct, this should be x, y, z, and w. All right, that's what I called my variables in this case. So that would be negative s, 2s, st, which is going to be s times negative 1, 2, 1, 0, plus t times 0, 0, 0, 1. So now we're looking at a basis. Our basis for W perp consists of two vectors, negative 1, 2, 1, 0, and 0, 0, 0, 1. Okay, so we started off with this brand new concept, W perp, but by just thinking about what it means. It took us back to solving, a homogeneous system. It took us back to chapter 1 stuff. Here's a general fact. If A is m by is square n by n. Oh, no, sorry, I don't need square. M by n. Then the orthogonal complement of the column space is equal to the null space of A transpose. Right, so here's a nice quick way to think about finding orthogonal complements. So let's just, let me give you a quick example. So let's let W. Sorry. Before I move on, this is true with respect to the dot product. So here. All right, so when you're working with the dot product and you say perp, right, the orthogonal complement, then this equation right here is true. Okay, so example is going to be, let's let W be the subspace of R3 defined by so I'm going to just write this out. W equals the set of all vectors x, y, z such that x plus y plus z equals 0. So what I'd like to do is find a basis for W perp. Right? So the instructions find a basis for W perp. Now, let's think about W. So elements, or vector, I should say vectors. So our solution vectors in W are of the following form. Well, so let's think about what they have to look like. They're column vectors, x, y, z, that satisfy this equation right here. So what that tells me, and I can write this in various ways, but if I solve for x, x has to look like negative y minus z. So they're of the form negative x minus y, no, negative y minus z, y, z. And then I can break this up, so this is going to be a y times minus 1, 1, 0 plus z times minus 1, 0, 1. So we've got a basis for W. And the basis for W is going to be negative 1, 1, 0 and minus 1, 0, 1. And so one way to think of W then, right, so W is the span of these, and so we could say, if we want, we could say W is the column space of the matrix consisting of those two columns right here. So W equals the column space of A, where A is the matrix with columns, first one, negative 1, 1, 0, second one, negative 1, 0, 1. Now, what are we trying to do? We're trying to find a basis for W perp, and from the equation, I just erased that equation, what we know is that W perp is the it's the orthogonal complement of the column space of A, which we know is the null space of A transpose. And we know how to find bases for null spaces. So let's look at A transpose. That's going to be minus 1, minus 1, 1, 0, 0, 1. Now I want to do some row operations here, get this thing in reduced row echelon form, and it looks like this when we're done. 1, 0, minus 1, and 0, 1, minus 1. 0, 1, minus 1. All right. So if we set up our, you can imagine creating an augmented matrix having a couple of zeros over here. Then what we can see is that we've got one free variable. Let's say x3 equals s, x1 equals s, x2 equals s. And so any vector in the null space of A transpose has the form, s times 1, 1, 1. And so our basis for W perp consists of the single vector 1, 1, 1. All right, so what's the point? If you have some subspace of Rn, you can think of it, in most cases, you'll be able to write it down as a column space, and then you can use the equation we have here to find the orthogonal complement of that particular space. So the idea is, if you have W, view it as a column space. If you're trying to find a basis for the null space, a basis for the orthogonal complement, it amounts to finding a basis for the null space of A transpose. Okay, I want to end today with one last fact. This is called the Pythagorean theorem. Of course, you've seen the Pythagorean theorem when it comes to doing Euclidean geometry, but it actually turns out to be true in general. So if V is an inner product space, and the vectors u and v are orthogonal, then the norm of the vector u plus v is equal to, squared, is equal to norm squared of u plus norm squared of v. Now, of course, the picture, this holds for a general inner product space, right? The elements u and v might be matrices, they could be polynomials, but I'm going to draw the picture just to get the idea as if, they really are sitting in Rn, or R2, the way I'm drawing this here. So here's u, here's v, and then remember, that's the vector u plus v. So what is that saying then? Length of u squared plus length of v squared is equal to the length of the hypotenuse, right? That completes the triangle. And the proof is easy. So let's see. Let's look at the length of u plus v squared. Remember, that means, the length squared is the inner product of a vector with itself. And then we can use the distributed properties here. And so what you'll get is length squared of, I'm basically foiling this out, length squared plus 2 inner product u with v plus norm squared of v. But if u and v are orthogonal, then this is equal to 0, right? And so we just get norm squared u plus norm squared of v. Okay, all right, that's a good place to stop. We got one more lecture left. Please, everybody, stay on top of things. We're almost to the end. All right, so we'll see you on Thursday. What's today? Tuesday? Yeah, we'll see you on Thursday.